Okay. So, today we will continue our discussion on dynamic matching and vertex cover from the last class. Let us briefly recall the algorithm that we were discussing. So, we discussed an algorithm and today we are supposed to present the analysis. So, what was the algorithm? You basically will partition the graph into log n levels. Partition the node set of the graph into log n levels as follows. You initially start with all the nodes in the graph and then you assign a weight of 1 over 2 to the power L to every edge. Then what happens is that after this assignment, the weight received by a node from the edges incident upon it will be between 0 and 1. Why? Because the highest degree a node can have is n, which is 2 to the power L. Just 1 second, I will keep the eraser here. Okay. So, after this assignment, you will partition the node set into two groups, say VL, and let us say this is VL, right, and let us say this is SL. Now, the nodes here now, their weights are between half and 1, and the nodes in SL, their weights are between 0 and half. So, basically the nodes here are approximately tight and the nodes here are slack. What you then do is you freeze the weights of the edges incident upon the nodes in VL, the nodes that are tight. Now, look at these edges. If an edge here is E prime, you just double its weight. So, W E prime will just become 2 times W of E. And after that what will happen? Initially the nodes here in SL, their weights were between 0 and half, right. So, after this doubling step, their weights will now become between 0 and 1. And again you will partition this SL into two sets. Let us call this VL minus 1, SL minus 1. The nodes in VL minus 1 will be the ones whose weights are approximately tight. So, their weights are between half and 1, and the nodes here will have weights between 0 and half. Then what we will do? We will just repeat this. Again just look at the edges E prime with both endpoints in SL minus 1 and double the weights of those edges. Sorry, W prime. So, again the weights here of the nodes will become between 0 and 1. You again partition it into two groups and continue like this, and this will go on till log n levels. So, at the end of this procedure, what we will get is this. This is level L, say this is level I, J, say this is V0, and let us say this is V minus 1. So, last class we saw that it will have the following property. The partition that we will finally get will have the following property, that if you look at any node in levels from V0 to VL, the weight of such a node will be between half and 1. So, this node will be approximately tight. If you look at any node in level minus 1, its weight will be between 0 and half. So, this guy will be slack, and finally, every edge will be incident upon the node set V0 to VL. So, there will not be any edge between two nodes here. This also we discussed in the last class. So, we will get that if we say that say V star is the union of the nodes from level 0 to L, then V star basically is a vertex cover. And the weights of the edges will be defined as follows. If there is an edge E whose one endpoint is at level I and the other endpoint is at level j, then its weight will be defined by the level of the higher endpoint. So, I here is the higher endpoint. So, its weight will be 1 by 2 to the power I. So, this was the thing we had. And now, how we saw that this structure will give us a 4 approximate vertex cover. So, V star will be a 4 approximate vertex cover, and these fractional weights that we are maintaining will give us a 4 approximate maximum fractional matching. Now, how do you maintain this thing in a dynamic setting? This also we saw in the last class. Basically, we will just implement the obvious greedy algorithm. So, what is the obvious greedy algorithm? Let us look at an edge insertion. Let us look at an edge insertion. So, okay. So, suppose this edge itself UV is being inserted. So, when this edge UV is being inserted, what will happen? This edge will get a weight that is 1 by 2 to the power I, and hence the weight of the endpoints will increase, and these endpoints weights can now become greater than 1. Hence, they will violate the invariant that we want to maintain. If that is the case, we will just mark these two endpoints U and V as dirty, and we have to fix somehow the dirty nodes. Similarly, suppose this edge is being deleted, what will happen? You just delete this edge. So, this edge had weight 1 by 2 to the power I. So, this edge now vanishes. So, the weights of the endpoints decrease, and hence the weight here say of U can fall below half, whereas the constraint was each. So, this node will no longer be tight, and again this node will become dirty. We need to fix the dirty nodes. So, basically we need a subroutine, a while loop that will just consider the dirty nodes in arbitrary order and fix them. And this was the while loop. While there exists a dirty node x, you do the following thing. This node x is dirty because of one of two reasons, right? Either its weight is too large or its weight is too small. So, if its weight is too large, then you just increment its level. So, here L of x denotes the level of this node x. Otherwise, the weight is too small, then you will decrement its level. So, this is the while loop, okay, and then you repeat. Now, what is the justification for this? Let us again look at this picture. Suppose case 1, so the weight of this node is too large. So, here is a node x, and look at the edges it has. So, suppose these are the edges incident upon it, E1, E2, E3, E4. So, E1 and E2 has the following property, that the other endpoints of these two edges lie at a level below x. Hence, the weights of these edges will be controlled by x itself. So, just look at this picture. Say here, if this edge is E1 and if this is x, the weight of this edge will be 1 by 2 to the power L of x. whereas the weights of E3 and E4, since the other endpoints of these two edges lie at higher levels, their weights will be controlled by these endpoints. So, x has no control over the weights of these edges. So, now if x goes up, what happens? The weights of these edges remain unchanged, whereas the weights of these two edges will drop. So, the intuition is if x goes up, its weight will drop. So, if Wx is too large, it should go up. Similarly, if Wx is too small, then it should go down, because if x goes down, then the weights of E1 and E2 will increase, because Lx is now decreasing. Okay. And the one other thing to note is that after one iteration of this while loop, x might still remain dirty. So, for example, it might be the case that this weight of x was much greater than 1 and you just incremented its level by 1 and it still remains greater than 1. Then it will again be considered in the next iteration of the while loop, you do not worry about that. The other concern is that while you are implementing this iteration, it might create some new dirty nodes. Why? Suppose x is going up, this is changing the weights of these two edges E1 and E2, right. So, what will happen to their endpoints Y1 and Y2? Their weights will change, because these two edges are changing their weights. So, Y1 and Y2 can become dirty, and if they become dirty, you again just throw them into the dirty list and consider them arbitrarily in the next iteration. Okay. So, this was the algorithm we had, and what we noticed was that when and if this while loop terminates at all, we just get back the original structure that we were looking for. So, this algorithm is correct and it gives constant approximation, but the point is to bound the update time. How can you show that this while loop will converge quickly? Okay. So, till this is what we discussed in the last class. So, this was, how much time did I take? Just one second. Yeah, this was a quick 10-minute recap of the algorithm of the last class. Any question? Because now what I am going to teach, it is going to be new about this. You have the algorithm in mind, right? Okay. So, how do you analyze the update time? Analyzing the update time. We will come back here later on. Let us first define the level of an edge as follows. The level of an edge is simply the maximum level among its endpoints. Now, what is the purpose of this definition? The simple point is, if the level of an edge is I, then its weight is 1 by 2 to the power I. Again, look at this picture, it should be obvious, right. So, the weight of an edge is completely determined by its level. Okay. Now, what is an obvious lower bound on the amount of work we have to do? The amount of work we have to do should be at least the number of times we are changing something in the fractional matching. And when are we changing something in the fractional matching? When the fractional weight of an edge changes, then we can say that we are changing something in the matching, right. And when does the weight of an edge change? When its level changes by definition. So, basically we can say that the work done by our algorithm is at least the number of times the levels of an edge changes, level changes of edges. So, is this thing clear? So, suppose you have a counter, you initialize it at 0 and then subsequently each time the algorithm is changing the level of an edge, you increment the counter by 1. Now, regardless of the data structure you design, you have to do total amount of work, that is the value of this counter. This is what I want to say, right. This seems intuitively obvious. So, now the point is we will design a data structure. Let us just first get the data structure issue out of the way. We will design a data structure where the work done will be actually proportional to the number of level changes in edges, and then later on we will try to bound this quantity. So, then these two issues will be completely separated out. The first thing is that design a data structure which does work that is proportional to the level changes of edges, and once you have designed that data structure, forget about the data structure altogether. Just look at this combinatorial process, what is going on, and in this process just try to bound the number of times the levels of an edge changes. Is this clear? Okay. So, what is a data structure? Where work done is roughly equal to number of level changes of edges. This is what we are going to design here. So, the idea is very simple. For every node V, just maintain the set of edges incident upon V whose level is I. Sorry, what am I saying? So, EV of I is just the set of edges that are incident upon V whose level is I, and maintain this thing for every node V and for every level I from -1 to L as a doubly linked list. This thing is maintained as a doubly linked list. And of course, what we will do is each edge will maintain a pointer to its position in these doubly linked lists, and the point being then you can insert and delete an element from these lists in constant time. Okay. Now, this is a pretty natural definition, right, that you are just maintaining these edges for every node. Now, what will this thing look like? So, the first observation is let us look at a node V that is at level I. So, V is at level I. Every edge incident upon V must have level at least I, right, because the edges are either of this form, say E1, E2, where the other endpoint is at a level that is at most I, in which case what will be their level? I, right. So, level of E1 and E2 is I. Otherwise, the edge is of this form E3, where the other endpoint is at above level I, and hence the level of E3 is greater than I. So, if you fix a node V at level I and look at this list, what you will find is that these lists are empty from level I minus 1 downward. In level I, EV of I just denotes the set of edges going down from V, and by down I mean weakly down, meaning that an edge of this form whose other endpoint is in level I also belongs to EV of I. And finally, for every level j that is above V, EV of j will consist of these edges whose other endpoint is at level j, and this thing goes on for every level from I plus 1 onward. So, is this picture clear? I want you to have this picture in mind all the time when thinking about the algorithm. Okay. So, now what do you want to prove? We want to prove that the work done by this data structure is number of level changes of edges. Then it suffices to consider just one iteration of the while loop, which I had written here. In that while loop, what were you doing? You were either incrementing the level of a node by 1 or you were decrementing the level of a node by 1. This was the elementary operation that you were doing. So, if we can show that for each such elementary operation this statement is true, then we are done, right. So, is this true for an elementary operation? So, suppose for example, case 1, V goes up from level I to level I plus 1. What is the work done by the data structure? What is the work done? The work done is the time you need to update this list. Okay. So, what is the time you need to update this list? How many lists will you need to update as V goes up from I to I plus 1? You only need to update, okay, you need to update two things. One, sum of V's lists and sum of V's neighbors lists. If a node is not a neighbor of V, nothing will change for that node, right. So, first let us look at V's neighbors. Who are the neighbors that will get affected? The neighbors only in EV of I will get affected. Why? Because look at a neighbor which is in EV of I. So, this is say U is in EV of I, right. And as V goes up, what is happening? This edge V of U were earlier part of its I list of U, and now it will become part of the I plus 1th list of U. Is this clear? On the other hand, look at a neighbor U that whose level is above I. As this edge goes up, what will change? It was this edge was earlier part of the jth list of U. Now, still it remains part of the jth list of U. It will not change, right. Okay. So, as far as the neighbors are concerned, work done for neighbors mean how much work you will do to update the neighbors list. That is going to be the size of this list, EV of I. And how will you do that? You will just, you know what EV of I is, you just go through all the edges in EV of I, and for every edge look at the other endpoint and inform him that, hey, now this edge is going up to I plus 1. That takes constant time per edge. Clear? Okay. What will be the amount of work that you need to do to update V's list? So, work done for V. You will need to do exactly. So, the work that you need to do to update V's list is just constant. Why? Because just look at this picture. So, this is I level I, this is I plus 1, and these are the levels upward from I plus 1 and upward. So, after V goes up to I plus 1, what will happen to V's neighbors list? First of all, EV of I will become empty. That is one thing. And the second thing is that EV of I plus 1 will become union of EV of I and EV of I plus 1. Let me say this. and then you set this to be empty. Now, do you see why the first step is correct? Because as V goes up here, what happens? These edges whose other endpoints are in I plus 1, they remain in EV of I plus 1. But these edges whose other endpoints were at I or below, they also now need to move to EV of I plus 1, right? Their levels have also increased. So, this step is there, and then finally, EV of I will become empty since V is now has gone up to a higher level. Now, how much time will you take to implement this step, these two steps? This step can be implemented in constant time, no? So, basically you have two linked lists, and I am just asking you to merge these two linked lists. So, if you store the start pointer and the end pointer, you just need to update constantly many pointers to merge these two things. And this step, how much time will it take? This will take time proportional to the size of this list, because you need to visit all the elements in this list and then delete them from this list. Okay. So, in both the cases you see that the total work done was the number of neighbors V has, which is at level I or below. On the other hand, what are the number of level changes that occur? It is again exactly equal to EV of I, right? Because the level of an edge does not change if it is not incident upon V. So, you only need to look at the V's incident edges. And of course, the edges that are incident upon V who are in EV of I, so these edges E1 and E2, their level of course changes. Why? Because earlier, yeah. Can you speak a bit loudly?
So, when we said, so when EV edges in EV of I moves up, right? So, actually we don't delete that list, we just append it, right, to EV of I plus 1.
Oh, okay, fine. You are saying that this will also need constant time, correct? Correct. Fine. But still it is overall EV of I, right, because this step will. You need to update the neighbors, no?
Yeah, but for each neighbor, is it constant? That is not clear.
Yeah, that is what I said, right. How are these lists maintained? Each edge maintains a pointer to the positions in which this node appears in this list. So, basically the assumption is that you can insert and delete an element from an in list in constant time. So, if you have this, then you can update it in constant time, right, for every neighbor in EV of I.
So, but then the list for each, so suppose EV of
So, okay, so suppose this is V, right, suppose this is U, suppose U is here.
Yeah. So, suppose it had say U1, U2 up to UL neighbors, edges in, so EV of I equals to U1, UI comma V, where I.
Okay, so this is say U1 and it has UL neighbors, fine.
So, now don't we need to update EU of, so the list corresponding to UI?
What is UI? U1, let us look at U1. The list, yeah. So, how much time will you take to update the list corresponding to U1? Just fix U1. How much time will you take? It is constant, right, because this edge E2 was earlier appearing in the ith list of U1 and now it will appear in the I plus 1th list of U1. So, basically you are deleting this edge from the ith list of U1 and inserting this edge into the I plus 1th list of U1, and insert delete operations take constant time in this doubly linked list. Okay. And so, okay, getting back to what I was saying, the work done is proportional to the size of EV of I, and the number of level changes is also exactly equal to EV of I, right, because the edges that are not in EV of I, their other endpoint are already in level I plus 1 or above, and their levels will not change. So, you can see that this statement is true when a node V goes up one level, and you can verify that this statement will hold true when a node V also goes down one level. Okay. The argument will be exactly similar. I am not going to go through this, but are you convinced about this statement, at least when the node V goes up? Okay. Any question? So, now what can we assume? We can just forget about the data structure altogether. So, as we said, we can just forget about the data structure altogether and we just try to bound the number of level changes. So, basically, suppose you have a counter like this. As I said, you initialize the counter to be 0 when you are starting with an empty graph. And then you increment this counter by 1 whenever you see after an edge changes level or gets inserted or deleted. And the theorem is, this is theorem 1. After T edge insertion deletions, the value of this counter is at most T log n. So, if we prove theorem 1, then we have proved a bound on the amortized update time. Is this thing clear? Okay. So, how to prove theorem 1? To prove theorem 1, we will just slightly change our algorithm. Okay. So, by slightly changing our algorithm, I just mean this, that earlier we were saying that a node V, when does this node go up? When its weight increases beyond 1, right? This thing remains the same. The only thing that will change is it goes down by 1 level. Earlier when it was going down, when its weight was dropping below half. Now, we will just give some slack and say that V goes down only if its weight drops below, instead of half, say 1/6. So, the point is that the first time you assign V to this level, say I, its weight was greater than half, and it goes down only after its weight has dropped sufficiently. Okay. And now, since 1/6 this factor, there is nothing special about 1/6. You can just have something smaller than half. Okay. That will do. Since this factor is within a constant factor of 1, the approximation guarantee will not get affected by too much. So, what will be the guarantee that you will be having? You will be having this guarantee, that look at these levels from VL to V0, look at this level V minus 1. So, in this levels, the weight of an node now is between 1/6 and 1, instead of being between half and 1. And here it just remains the same, the weight of an edge is between 0 and half. So, this will still give you a constant approximation, because this is still going to be an approximately maximal fractional matching. Okay. So, now we will see why this is needed. So, what is the intuition behind analyzing the update time? Why should the update time, why should the value of this counter be small? Okay, here is the first attempt. Suppose we say that during the lifetime of an edge, what is the lifetime? Look at the time when it is inserted and the time when it is deleted. This interval is this lifetime. Suppose we say that during the lifetime of an edge, its level can only go up. Okay. If we say this, will we get this bound if we can prove that? We will, right? Because after T edge insertion deletions, because that then means we are considering at most the lifetimes of T edges, and for each edge, since its level can only go up, it can start at -1 and go up till L, and L is log n. So, each edge can contribute at most log n to the value of this counter. Okay. So, if we could prove that, this will prove theorem 1. However, that is too good to be true, and you can easily come up with examples where this is not going to happen, meaning the level of an edge goes up for some time and then again comes down. It is not difficult to see that in the algorithm this can happen.
So, it will come down at most by log n, right? So,
But it can again go up and again come down.
so but then, so do you mean for, so if we fix one edge insertion or deletion, for that it can go up by log n or go down by log n?
In general, if you look at the lifetime of an edge, it can go up and down arbitrarily many times. So, basically, if the levels of the edges were only going up, what would it have meant? It would have meant that each edge contributes at most log n to the value of this counter, because the level of an edge cannot go up more than log n times. But if the levels can both go up and come down arbitrarily, there is no bound on the contribution one edge is making to this counter. That is the point I want to make.
Are you saying that for, say, one edge insertion, the edges can go arbitrarily up or down, like it can, I am
Yeah.
not understanding.
No, so okay, what is this point of confusion?
So, you said that this is too good to be true, right? That,
Yes. So, what is too good to be true? What is the statement that I meant?
okay. So, you said that one edge can go, so the number of levels it can go changes log n, right? It can go either log n up or log n.
No, I just said suppose it just goes up.
Okay.
Yeah, that was the statement, and I said this is too good to be true. So, yeah, what is the confusion? I just want to understand this.
I don't understand why this cannot be true. So, like, why you are claiming that this is too good to be true?
If I show you an instance where the level of an edge drops, that nullifies my claim, right?
But then also it will go down at most by log n.
And then suppose it again goes up.
But can for one edge insertion it can go up by log n? I mean, the number of level changes, can it be more than 2 log n?
Okay. So, I think you are confusing between two separate aspects. One is that after one particular edge insertion, look at how many times, look at by how much this counter is increasing. What you are arguing about, it pertains to claiming that after one edge insertion or one edge deletion, this counter cannot go up by more than log n times. Is that correct?
Yes, that's what I.
Okay. Now, if what you claim is true, this will imply a worst case update time of log n. Do you agree with that?
Per edge insertion.
Yes.
Yes.
okay, but that is clearly not true. So, for example, it's suppose you had a node here, it's okay, I cannot give you a concrete example, but I can tell you what can happen. Suppose this was a node here and you deleted sufficiently many edges incident upon it. So, what will happen? Its weight will drop.
No, but we are talking per insertion or deletion, right?
Yes, but look at the last time when this happens. At some point in time its weight will drop, right? Just look at that event when it drops. Do you agree that there can be a cascading effect? I mean, this node V will then come down because its weight is too low and it comes down. And what will be the effect of this node V coming down? If V comes down, what will be the effect of the other nodes on the other nodes? Might increase. So, what will be their tendency? Their tendency will be to go up, and when they go up, what will happen? Their neighbors' weight will decrease. So, their neighbors will now tend to go down, and when their neighbors go down, their neighbors what happens to them? They want to go up, and you do not know how long will it take before this thing stabilizes. So, that is what I am saying, that there is no obvious way of arguing that after each edge insertion and deletion this counter will increase by at most log n times. Is that clear what I said? Okay. Now, instead what we will argue is this: although there are some bad events, let us say a bad event happens when the level of an edge drops. That is a bad event, right? Because if only the levels of the edges were increasing, then we would have had this bound. Do you agree with that, Akanksha? No, do you agree with this statement? Because if you do not get this, you will not be able to follow the next part. Suppose if it were true that the levels of the edges can only increase, then this theorem is true. Do you agree with this statement or not? Okay, so how do I explain it? Do you see it, Niranka? Yeah, so look at this counter. Suppose the levels of the edges can only go up. Now, I am asking you one question. One particular edge, not one particular edge insertion, I am not talking about that. One particular edge, how much can it contribute to this counter?
Yes, one particular edge can contribute to at most log.
Okay. Now, we are dealing with T edge insertion deletions. So, what will be the total contribution to this counter?
So, okay, so you are saying that when levels are going up, there will be no cascading effect that you were talking about.
Yeah, that is an implication, but the point I wanted to make was that the value of this counter will not be more than T log n.
If there is no cascading effect,
There can be cascading effect. I mean, one edge goes up, maybe it enforces some other edges to go up, and that enforces some other edges to go up. There can be some arbitrary cascading effect. But if I gave you magically some different algorithm where the levels of edges only goes up, okay.
so suppose if we look at a vertex which is at lowest level, and suppose it has some L neighbors above. So is this true? Because
Okay.
if it has
Okay, can I just write it down like this? What is C? This sum is not over all the edges at a particular instant in the graph. This sum is over all the edges that were ever inserted. So, if an edge is inserted and deleted and then again inserted, this counts twice. Okay. Now, what is this C? This C is that look at the lifetime of this edge E. How many times did it change its level? Do you agree about this equality? Yes or no?
C is the
I defined C, right? So, do you agree with this equality? Now, if the levels of edges only go up, can we say that each C is at most this? Can we say this? You can, right? So, then what does this imply? It implies that C is at most, you sum over these edges and each time you get at most log n contribution. And how many edges are you going to sum over here? Yeah, why not? You are confused that this is not.
completely confused because I'm not understanding like why other edges will not get affected. Maybe it's like some stuff. So at least to me, it's not clear. Like if cascading can happen on the previous case we were discussing, why only 3 contributions?
Okay, can we just take this thing offline? Are others on board with me on this? Yes? Okay. Let us take this thing offline. Okay. So, what I want to do is that, let me see how much time I have. Okay, since we started a bit late, I will just go a bit over time. So, what I want to do is this. First, I want to give a high level intuition as to why the update time is t log n, and please stop me if you do not understand how I am defining this counter, because if you do not understand how this counter is being defined, you will not going to follow at all anything later on. So, the first thing I am going to give you is a high level intuition as to why this should be true. Second, we will show a formal proof using potential function. Okay. So, now I am just in the high level stage, the intuition. So, the intuition is this: you start by noting that if the levels of the edges were only going up, you are good. So, now you have to account for the fact that sometimes there will be some bad events. What are these bad events? The levels of some edges are going down. However, you are going to show that for some such bad event to occur, so suppose you noticed there is a bad event k, there is a bad event where k edges are decreasing their levels. You have to say that for that event to occur, in the past, a much more than k number of edges must have increased their levels earlier. So, it is as if intuitively you are saying that yes, the bad events can occur somewhere in between, but if you look at a sufficiently long time horizon, on average the levels of the edges are always increasing. So, this is a very vague intuition. Does it make sense? Okay. And now, how can you show that? That is why this, that is where this slack of 1 over 6 will come into play. So, look at this bad event. So, okay. So, look at a bad event. So, what is a bad event? Some edges are decreasing their levels. How can this happen? Only when a node is decreasing its level by 1, that is the elementary operation we are concerned about. So, suppose here is this node V at level I, and now V is going to go to level I minus 1. Now, look at the previous time instant when V came to level I. Okay. So, suppose t is the time instant when V came to level I, and now we are looking at time step t prime where this bad event is occurring. So, V is coming down to level I minus 1. So, the first point is intuitively when V came to level I, we will ensure that its weight was actually between half and 1. However, under this revised algorithm, when this bad event is occurring, we know that the weight of V is less than 1 by 6. This means that during this interval, WV actually has decreased. It was earlier at least half, now it is below 1 by 6. So, WV dropped by at least half minus 1 by 6, which turns out to be roughly equal to 3 by 6, 2 by 6, 1 by 3. So, now during this time interval, WV dropped by 1/3. How can this happen? It can happen because of only two reasons. What is the reasons? Some edges incident upon V got deleted, that is one. What can be the other reason? Some edge incident upon V increase its level. So, suppose this guy was VU and now U goes somewhere up here. Earlier the weight of this edge was 1 by 2 to the power I. Now its weight is going to be much less, and similarly for U prime, because U prime now increased their level, the weight of this edge has dropped. Okay. But the observation is weight of every edge incident upon V is at least 1 by 2 to the power I. That is correct, right? Because the weights of these edges whose other endpoints are below I, that is exactly 1 by 2 to the power I, and the weights of these edges, if U is at say at level j, what will be the weight of this edge? 1 by 2 to the power j, right? And 1 by 2 to the power j is, sorry, it is the other way round. 1 by 2 to the power j is less than or equal to 1 by 2 to the power I. So, weight of every edge incident upon V is at most 1 by 2 to the power I. Now, what can you say? Whenever for WV to drop by at least 1/3, how many of these edges must have either gotten deleted or increased their levels? For this event to happen, you have to say that then at least 2 to the power I over 3 edges were either deleted or increased levels. That is correct, right? Because each edge incident upon V makes a contribution that is at most 1 by 2 to the power I. So, for V's weight to changed by delta, at least 2 to the power I times delta. So, this is, I hope this is clear, this I mean 2 to the power I by 3. Many edges must have either increased their levels or gotten deleted. Yes.
And if it goes up, it makes a lesser negative contribution.
Yeah. So, this thing is a conservative estimate, it can be even more than that, but I am saying at least, right. Okay. And now, when this bad event is happening, how many edges are decreasing their levels? Only the edges that are below, they are decreasing their levels, right, for this bad event. And how many edges can there be? At most 2 to the power I by 6, because each of these edges have weight 2 to the power I. sorry 1 by 2 to the power I, and the weight of V is at most 1 by 6. So, there can be at most 2 to the power of I by 6 many edges decreases their levels at the bad event. Is correct? Now, just compare these two numbers. We are saying 2 to the power I by 6 many edges are decreasing their levels at the bad event, but for bad event to occur during this interval 2 to the power I by 3 many edges increased their levels or got deleted. So, there is a significantly larger chunk of edges which have increased their levels prior to this event to trigger this event. So, on average the levels of the edges are only increasing. Is the intuition clear? Okay. Now, the formal proof, and yeah, it will take another 15 minutes or something. So, now we introduce another technique for analyzing the update times of dynamic algorithms, the so called potential function method. And this is by no means unique to dynamic algorithms. Even in static data structures, you often use potential functions to argue about amortized update, amortized say query times or something. Okay. So, what is a potential function? Argument, and we will see one other use of potential function in the next lecture in the context of a different problem. Okay. So, somehow most of the times the use of potential function is quite magical, in the sense that if you ask me why did I come up with exactly this potential function, I really have no idea. It is almost like some divine inspiration or black magic. But ideally what happens is that you have some high level intuition as to why it should work, which I just presented to you right now. And then you have this high level intuition on the other hand, and start with some very coarse potential function and see if you can use that. If not, then using the intuition as your guidance, you try to modify the potential function by doing some fine tuning, and finally you come up with something that works. Okay. So, this part will be a little bit boring, but it will be instructive. We will just go through and see that this potential function actually works, and if you spend enough time, you will be able to convince yourself that it basically captures the intuition that I mentioned previously in the past 10 minutes. Okay. So, what is the potential function? So, we associate a potential with every node and every edge. What is the potential associated with an edge? It is defined here. So, look at an edge u v, recall that the level of this edge is maximum level among its endpoints. So, if this edge is at level I, the potential of this edge is epsilon times L minus I, where L is the highest level and epsilon is some tiny constant. You can think of it as 1 by 10 or 1 by 20, does not matter. Okay. Now, the way you will visualize this is as follows. So, suppose there is this edge at level I. What does this mean? Its higher endpoint is at level I. So, the edge can look like this. It is as if this is the case, then look at the levels above I plus 1 to L. Then it is as if someone has stored epsilon coins or epsilon tokens for this edge to grab when it goes up to level I plus 1, I plus 2 and so on. It is as if at each level greater than I, someone has placed epsilon many tokens for this edge, and when this edge goes up, it will just consume that token. Just visualize it like this. Okay. Now, there is also a potential associated with each node. So, suppose a node is at level I, then what is its potential? it is max of 0 comma half minus the weight of this node, and you will see that the half minus the weight, this half is coming from the fact that when a node first settles at level I, its weight is supposed to be between half and 1. So, at that time what will be this potential? This will be 0, right, because the weight of V will be greater than half. Does it make sense? And then if its weight decreases sufficiently, its weight decreases below 1/6, then we might have to decrement its level, and when we are decrementing its level, then it releases quite a lot of potential. Is that correct? Okay. So, when the level of a node is being decremented, what will be this WV? By definition it will be at most 1/6. So, at that time this node has positive potential. However, when it was first put at that level, its weight was between half and 1. So, the potential was 0. Okay. Okay. So, I made a small mistake here, it is going to be times 2 to the power I. And this 2 to the power I, you have to relate it to the fact that each edge incident upon this node V has weight that is at most 1 by 2 to the power I, and that is some vague reason why we have this multiplicative 2 to the power I term here. Okay. So, now the point is that somehow we have a potential associated with each node and each edge. So, phi of V will denote the total potential associated with all the nodes, phi of E will denote the total potential associated with all the edges, and delta will denote the sum of the node potentials and the edge potentials. Okay. Now, initially we start with an empty graph. What is the total potential? We will just keep track of this total potential and what it does. What is the total potential in the beginning? The edge potentials are 0, right? There are no edges. So, no edge potential. What will be the node potential? Each node is sort of at level 0 and weight is 0. So, WV is 0, right, because it does not have any edge. So, what is this node potential? This is going to be some constant, right, half minus 0. So, max of 0 comma half minus 0 is half times this is 2 to the power 0, this is 1. So, each node will have potential that is roughly half or something. So, the total potential in the system initially is theta of n. Okay. Now, what we will show is, okay, the second condition to note is that by definition at every time step the total potential is non-negative, it is at least 0, because of the max term here the node potential is always non-negative, and by definition the edge potential is always non-negative. Okay. And now, what we are going to show is that after each elementary operation, what is an elementary operation? A node moves up one level or moves down one level. The drop in the potential is going to be at least the number of level changes of edges. Okay. So, what does this mean? Is you can think of this potential as sort of a bank account. Someone has initially put say n rupees or n dollars into this bank account, and then it is guaranteed that this account will never have negative balance. And then it is also okay, and one other thing is that what will the insertion and deletion of an edge do to this potential? Let us just calculate this thing, right. So, insertion and deletion of an edge. So, deletion is like this. So, this is say level I, this is level j, this was the edge and this edge got deleted. Just after this deletion, what will happen to the edge potentials? How will they drop? They will drop by At most epsilon log n, because what was the edge potential associated with this edge? L minus I, right, and L minus I was at most log n, and after the deletion of this edge, this particular edge potential will vanish. Make sense? And what will happen to the node potential? So, let us look at this node V. How will this change? You just need to look at by how much the weight of V will change. Let us say this is I and this is j, so that there is consistency in the notation. So, V is at level I, this is at level j. So, by how much will the weight of V change if you delete this edge? 1 by 2 to the power j, right. So, W V changes by 1 by 2 to the power j. So, by how much will this potential node potential change? It is going to be at most 1 by 2 to the power j times 2 to the power I, that is the worst case. So, the node potential will change by at most 2 to the power I by 2 to the power j, and you can note that this is less than or equal to 1. Okay. So, what do you know? You know that after an edge deletion, the total potential changes by at most epsilon log n, right. On the other hand, after an edge insertion, what happens? Let us look at the edge potential again. Suppose this edge was now being inserted. So, this is now say insertion. So, a new edge potential is being created for this edge, and how much is being created? It is again at most epsilon log n, right. And similarly, you can show that the node potential will also change by at most 1. So, in effect you can show this. Let me just write it down as statement 4, so that we can have all these things together. So, 4, each edge insertion deletion changes the total potential by at most order log n. Seem confused. Is this part clear, this statement? So, you are, so the point is this, the high level point is this. If you think of this potential as your bank balance, it is going on like the following way, in the following way. You start initially with theta n balance in the empty graph. Then the process is as follows. After each edge insertion deletion, somebody deposits at most log n dollars or rupees into your account. It can also withdraw something from your account, but the point is that the change is at most log n. Okay. And you know that the account always has non-negative balance, right. And finally, condition 2 says, which we are going to prove now, that after every elementary operation, some amount of balance is withdrawn from your account. This is drop in the potential, and this amount of withdrawal is proportional to the number of level changes in the edges. So, then you argue that for T edge insertion deletions, what could have been the total deposit into my account? By condition 4, it can be at most T log n, and you know that the total withdrawal from your account is proportional to the total work done by the data structure, and you know that the account has non-negative balance. So, that means the work done by your data structure, what can be the total work done by your data structure? It can be at most the total amount that was deposited into your account. What was the total amount deposited into your account? It is n, that is the initial balance, plus the total number of deposits during this t age insertion deletions, this is t log n. So, now what does this mean? It means that if t is greater than n, this is order of t log n if t is greater than n. Okay. Now, I have this condition that t greater than or equal to n here, because I have this initial condition of theta of n, but you can get rid of this using some slight tweaking. Okay. But for simplicity I am not talking about it. Okay. So, now are you convinced if we just prove point 2, then we will have log n update time for our data structure. Let us just prove part 2 and it will take 10 more minutes. Okay. So, part 2, proof of 2. What can I erase? I can erase 4 and 3, right, because we are not going to need this, we are just going to concentrate on 2. So, let us just erase 4 and 3. So, there are two cases. Case 1 is V is going up a level and case 2 is V going down a level. So, let us just consider case 1. So, this is V, this is level I. Okay. So, can you see what is going to happen to the edge potentials when V is going up from I to I plus 1? Is going to be epsilon times why? Because which are the edges that will get affected? The edges that are incident upon V. Now, if an edge is incident upon V and this other endpoint is at level I plus 1 or above, will its edge potential get affected? No, because its level is not going to change. But if the other endpoint was here, say this is E1 or say if it was here E2, was at level I or below, then by how much will it drop? Earlier it was epsilon times L minus I, now it is going to be epsilon minus times L minus I plus 1. So, it is going to drop by epsilon. So, it is as if this edge is going up. So, it is as if just gobbling up the epsilon many coins that were stored for it at this level. Okay. So, the drop in the edge potential is going to be epsilon times E V of I. Okay. Now, what is the drop in the node potential? So, drop in phi of V, let us just look at the total drop in all this node potential. So, look at V, what will be the new node potential of V? The point is that since V is going up, what do you know? You know that V's current weight has to be greater than 1, otherwise V will not go up from level I. This is part of the algorithm. V is going up because V's weight has increased beyond 1. Now, if V's weight is beyond 1, when V goes up, what will be the new weight of V? So, this is old weight of V. The new weight of V has to be at least half, no? Because when V is going up, what is happening? Some of its adjacent edges are reducing their weight by a factor of 2. So, if you look at an edge E 1 like this, earlier it was 1 by 2 to the power I, now its weight is 1 by 2 to the power I plus 1, and the remaining edges, their weights are remaining fixed. So, if V goes up a level, its total weight can drop by at most a factor of 2. So, V's new weight has to be at least half, and if V's new weight is at least half, what will be phi of V? That is going to be 0. So, that means that the new value of phi of V is going to be 0. And for any other node, any other neighbor of V, because if a node is not a neighbor of V, its phi value does not change. If a node is a neighbor of V, what is going to happen? Its weight can only decrease, because the levels of some edges are increasing. So, the weights can only decrease. Now, if the node weight decreases in this expression, the potential can only increase. You do not have to check how much the increase is, the potential can only increase. Okay? So, for other edges, for other nodes u not equal to V, phi u only increases. So, for nodes that are other than V, their node potentials can only increase, and what happens to the node potential of V? Its final node potential is 0. What was its initial node potential? You know that W V old was also greater than 1, right. So, its initial node potential was also 0. So, V's node potential did not change. So, drop in all the node potentials is going to be sorry, I just slightly messed it up. Let me do the following thing. We will not consider the other case when edge V comes down. We will just go through the proof of this case. Let us just write down what we know. We know this. Let us say this is statement 1. So, this is S 1, and we know that the potential of V does not change. Let us say this is statement 2. So, what we want? We want to now show, we want to lower bound the drop in the edge potentials. If this thing increases, okay, let us do the following thing. It is quite some time now, 1:16. I do not want to spend time staring at the board trying to fix this thing, because the problem here, you can note what the problem here is, right. I was thinking that if it were the case that the potentials of V's neighbors only decreases, then we would have been fine. what do we want to show? We want to show that the drop in the total potential is at least the number of level changes. We have shown that the drop in the edge potentials is already at least the number of level changes, right. So, if we could show that the drop in the node potentials on the other edge of the other nodes is non-negative, then we would have been done. But here we have found out something else, that the node potentials of its neighbors are increasing. So, we need to bound this increase and show that this thing actually is less, this increase is less than the drop in the edge potential, that we need to show. And for that I need to just redo this thing, I just made a silly mistake there. So, it is 1:15, let us stop here, we will continue next class.